Yeah, now I would like to start with our first presentation. Robert will introduce us to the causes of heat waves on which you have a strong research focus. You have worked for the University of Sorbonne as a data scientist, but now you are working for a company called Ecomonitor. Perhaps you can start to tell us at the beginning a bit about Ecomonitor. What's it about? Robert, please.
Christoph, certainly I'd be happy to. So let's see if this works. Are
Yeah.
we seeing a presentation? Fabulous. I had to quickly do some troubleshooting here on my old Ubuntu computer is it's not going to make it to the new year, but it's going to make it for today. So very briefly, Ecomonitor, we are effectively a solutions house, as Christoph mentioned, that is a startup creating a hybrid modeling system that combines system dynamics with ecological modeling to better put a quantitative dollar value on the co-benefits of nature-based solutions. So going beyond just carbon and biodiversity credits to better inform any investors of what actual impact their project may have, or conversely, for project managers to better allow them to attract more financing because they can show the larger range of benefit that their project will have. Specifically, we're looking to onboard one or two mangrove projects at the moment. So if you are a project manager in the mangrove space, please do reach out to me. My contact will be at the end of the talk. I think we could have a very interesting conversation. So without further ado, we will move on to the task at hand, and that is to describe basically what are heat waves. Or in this case, good news for some, bad news for others, what are marine heat waves? I'll be sticking within my area of expertise for this talk, but because I'm focusing just on the foundation definition, which is the statistics and the physics, this applies more or less to heat waves in the air, so on land that affect people, or heat waves in the ocean. So very simply, marine heat waves, there's a lot of different definitions. But for this talk, to keep things simple, I'm using the most frequently used definition, which comes from a paper by Hobday et al. In 2016, with the quote given there. And generally speaking, I can say in the heat wave community that this definition qualitatively, not necessarily quantitatively, is agreed upon by most parties. But when we get into the exact statistics of how we want to quantify a marine heat wave, there is some disagreement, and that's good. Debate is very healthy, and there should not be one agreed upon definition. Though the consensus has basically come out, I'm happy to say, that everyone is willing to agree to disagree, and that's fine, because it depends on the question at hand. And in this case, because I'm presenting global statistics based on what the future of marine heat waves will look like against the past, I'm going to be using this definition. If there's any questions, I'm happy to discuss that later. So what does that actually look like? Very simply, a marine heat wave is when the temperatures, which are this black squiggle, you'll notice there are no numbers. This is just a schematic. We have time on the x-axis and temperature vaguely on the y-axis. When temperatures exceed a threshold for 5 or more days, we call that a marine heat wave. We decide that it's a threshold because first we have the seasonal average, which is the average temperature on any given day for the last 30 years. And that's this blue line here. Then, if anything is an exceedance of the 90th percentile, right, which is the top 10% of temperatures above that blue line, then that's this green line here. And then we say it's a marine heat wave. So it's as simple as that. And you can do a lot with these statistics, but the calculation itself is very straightforward. And that's one of the reasons why it's used so broadly. There's no physics, there's no this is or that's involved. It's just a pretty straightforward calculation. You can do it by hand if you want to, if you really have nothing better to do with your time. So why should we care? Why should we care about some statistical definition? Well, it's because thanks to this statistical approach to defining this event, we know that their duration and intensity are increasing globally. We know that these events have already had dire consequences on the natural world and will likely continue to do so. And something that we don't think about often when we think about this sort of research, at least some people don't, myself included, is that a marine heat wave, an extreme temperature event that happens now, is a very good snapshot, a good picture of what that area will look like in the future, 20, 30, 50 years from now. How an ecosystem of today responds to a heat wave is going to be a good indication of what that same area is going to look like in the near future. And this is why we like to study these things. And this is why it's so important to look at these future projections. And if we want to sum all of this up into just one figure, where have things been and where are they going? I think it can be done just with this one image. And so what we're looking at here is two different possible futures. On the left-hand side, we have a medium emissions projection, which is the RCP 4.5. On the right hand of your screen, you're seeing RCP 8.5, which is a high emissions scenario. We're much closer to the 8.5 than the 4.5. On the x-axis is years from 1850, so very far in the past, up until 2100. On the y-axis, we have the average number of days that the ocean experienced a marine heat wave or is projected to experience a marine heat wave. We can see historically that because marine heat waves are natural, they do occur naturally, they have in the past, you get maybe 20 days of marine heat wave activity over the whole ocean for any given year as an average, rough estimate. With climate change, because the planet generally is warming, we start to see this sort of hockey stick, right? So starting around 2005, we started to go up, and we're going up and up and up. And the projection is that almost regardless of our emissions pathway, we're going to get close to that constant 365 days per year marine heat wave. And that's that dashed line there that shows 365. But what's really important is the difference in the intensity of these events. And so I won't get into the statistics on how these categories are calculated, but qualitatively, what they mean is moderate, yellow, means that will have an impact on a given ecosystem, but generally, once the heat wave ends, it'll go away. The ecosystem will naturally recover on its own, almost all the time. Orange means that it's going to have some sort of impact, but usually it can recover by itself. Potentially, it might need a little bit of help. Red, severe, means that it's going to have an effect, and it's probably going to last. Whereas, apologies, my camera's being a little funny. Whereas the dark red, almost black, means that ecosystem is effectively going to be impacted so severely that when it does recover, it will recover as something else. And I have an example of that later in the talk. And so this is all relevant because this means that if we can get our emissions under control and we get closer to this 4.5 pathway, which is viable, it's not unrealistic, we could limit the ocean to be experiencing only those categories moderate and strong, about half of the ocean. And that's adaptable. We can manage that. Whereas if we have these really high emissions, then at least 2/3 of the ocean is always going to be experiencing an extreme heat wave almost the whole year, which effectively means, and this is a broad generalization, it means that 2/3 of the ocean by 2100 will have a different ecosystem than they have now. To be clear, that's not to say that 2/3 of the ocean will become a desert. Life finds a way. But it is to say that 2/3 of the ocean will likely look very different from the way it is now, meaning different fisheries, different things we can do to exploit the ocean, different ways it can support us. Different might mean good, but it might mean bad. And we don't know which way it's going to go. And that can be problematic. So with that picture in mind, and don't worry, this is not all doom and gloom. That is not the point of this talk. And I'm not interested in just talking about doom and gloom either. But this background is necessary to frame where we're going. So what causes marine heat waves? Well, physics. Don't worry, I'm not going to throw any horrible equations up on the screen. I haven't worked in physical oceanography for a long time. I'm very happy to be able to say that. Sorry for any physical oceanographers on the call. But these are the terms, which is not to worry about them so much. Because I think that this quote, which I did not write, but I think does a very good job of explaining the situation, sums it up better than any physical equation could do. And that is simply that we thought we had defeated the natural world because we defeated the animals and plants. But it turned out that they were only our fellow travelers struggling to survive. The real world is dust and fire and flood and hard radiation. It never sleeps and it always hungers. Marine heat waves are effectively driven by the physics of the ocean, which is the flux of temperature into the surface, the mixed layer temperature at the surface, and then movement of water. And because many of these components are driven by the greenhouse gases accumulating in the atmosphere, this means that the major issue that's increasing the duration and intensity of marine heat waves is our anthropogenic impact. It's because we're emitting so many greenhouse gases in the atmosphere, we are forcing the increase in marine heat waves and the destruction to the ocean. We have no one else to blame for it but ourselves. So, on that cheery note, what's a brief history of the marine heat waves we've seen? So let's not talk about statistics or physics. What actually has happened in the past and what impacts did it have? Well, we kick off this little story in the Mediterranean Sea. In 2003, which anyone here who was living in Europe at the time will recall, was an incredibly hot year on land, in the air. I think something like 70,000 people died across Europe. It was crazy. It was a really horrible event. And it was one of the first times when we started to realize collectively that, maybe this whole climate change thing isn't a conspiracy. Maybe it's real, right? But then things kind of cooled off for a while. It wasn't several more years until 2011 when there was still on record one of the most intense, longest lasting open ocean marine heat waves off the coast of Western Australia. This wiped out hundreds of kilometers of kelp forest, which have not come back. This is an example in the literature, and there are a few now, of extreme category marine heat waves that wipe out a local ecosystem. And when it's replaced by something else, generally something that is like warmer water. So in this case, it was all kelp forest, which is the little picture on the left of your screen. And it was replaced by tuft, sort of scrub, and coral reef, interestingly. And that's the picture on the right, but it's not as productive. Directly after that, in 2012, was an event where we had the Northwest Atlantic Ocean off the coast of Eastern Canada, had an enormous marine heat wave that happened right when the lobster fishery was starting to get going, and it turbocharged the lobster fishery. It didn't kill them, it made too many of them. And it actually destroyed the lobster market because there were too many lobsters. It was also the first documented case of a climate event in the Northern Hemisphere causing international tension between two countries, because you had fishermen and lobstermen, technically is what they're called, in Canada and the United States fighting over the lobsters. Finally, to wrap off our history tour, we have the blob. This is actually what it's called in the literature. This is a scientific name. It's published in a lot of papers. If you want to look up the blob, not the movie, but the heat wave, you can find a lot of journal articles about this. And depending who you talk to, this event lasted for 2, 3, 5, 10 years. It's basically the entire northeastern Pacific Ocean. And there's a lot of things that cause this, but it's effectively a semi-permanent feature now. And it can be so bad and widespread that it can kill whales. You'll have whales starve because they can't find food and they'll wash up on shore. This is the scope of the events that we're talking about now. And this is already 10 years that this has been going on. So where are we at now? Right? So 10 years on from the blob, this is a global summary of marine heat waves. This summarizes the historic extent of these events. And I'll walk you through what these two figures are showing. So these are the data from 1982 to 2023. These are from the NOAA, which is an American organization, and their OISST satellite temperature product. So the climatology period, meaning what is the average temperature we expect, is from 1982 to 2011 for the people that are interested in the statistics. And what we're looking at on the left-hand side is the average number of days that the ocean is experiencing a marine heat wave. So the x-axis is years, and the y-axis on the left is the number of days. If this were to be 365, that would mean the ocean is experiencing a constant marine heat wave. At the moment, 2023 was the record setter at about 110 days on average. So we're getting close to the halfway point now. The right-hand side of the same figure, you'll see percentages. And this is just the same way of thinking of the statistic. You can either think of it as the number of average days per year, or as the percent of the ocean on any given day that is experiencing a marine heat wave, right? So 110 days on average is about the same as 32% of the ocean on any given day experiencing a marine heat wave. And it's the same number, but certain people like to think of it in different ways. So I like to show it as both. The panel on the right is showing us the total surface coverage of the ocean that experiences a marine heat wave on any given year, right? And this doesn't seem to be increasing that much, which might seem odd because on the left-hand figure, we see this crazy logarithmic uptake, whereas on the right, we're not seeing very much difference. And this is because marine heat waves do occur naturally. It's a normal phenomenon. There's nothing wrong with it. In fact, it's something that is competitively advantageous for some species and not for others. It's just that now we are turbocharging the length of these events and the intensity of the events. So let's have a look at what these years might look like. To give a better example of, globally speaking, what does marine heat wave coverage look like? So what we're looking at here is 1985, which is the lowest year on record. And this is a map of every single part of the ocean that at any point during the year experienced a marine heat wave. We see that this was about half, right? It's about 50%, a little bit less. There's big patches where it does and doesn't occur. The bottom left panel shows us what percentage of the ocean was experiencing a marine heat wave on every given day of the year. So from January 1st to December 31st. And you can see on average is about 1 to 5% on any given day. The number of days where we see a marine heat wave, it was about 10 days on average over the whole ocean. And then the final panel, panel D, is just the same as we saw before. It's just the same as panel B here, just to give a historic reference. If we look at 2023, we see a very different picture, right? Now we see basically the entire ocean is experiencing marine heat waves, and they're very scary looking. They're not these light little fluffy yellow marine heat waves drifting across the surface. It's now constant orange, red, dark red marine heat waves. On average, we see 20 to 40% of the ocean experiencing a marine heat wave on every single day. And we see about 110 days of events, right? Don't be deceived by the similar shape in panel C. It's the y-axis that matters. That's the average number of days. And again, this is the historic context. We have the records for 2024. The year isn't over yet, but we're already at about 120 days on average of marine heat waves, and it's only on the way up. Though we do see it seems to be ticking down now, which is interesting. So 2024 is likely going to be hotter. It already is, basically. But what does that look like over time? So if we go back all the way to the beginning of the record, and my internet works, we will see that we have events at the beginning. Oh, wow. Okay. Interesting. This might not work. My computer is having some issues, as you can see from all my video not working. This is on YouTube. If you do look up annual marine heat wave summary, you will be able to find this. It's publicly posted. Oh, no, it doesn't want to work. If we were to scroll through this, though, we see the progression over time and how you would see that in the beginning of the time series in the 80s and 90s, you had very mild moving patches of marine heat waves. Sometimes there's none, sometimes they're thick, but it's not constant coverage. And it's in the mid-2000s that we start to just have constant marine heat waves. And then around the mid-2010s, you just have these really intense red spots that start to appear. So we'll move on from that. And that's the state of things. Things are getting bad, but there are an immense amount of resources that are available for anyone who is interested in being part of the solution. And I'm not going to get into those today. because there's 3 very good talks coming after me, and I'm looking very much forward to what they have to say. So I would like to highlight some of the resources that are available. These are all open source and openly available for anyone to work with. So the first is an interactive demo. So this is for anyone who doesn't know what the marine heatwave definition is, and at this point, they might be too afraid to ask, right? So this is a nice, safe space where you can go and play around with the demo. You can upload your own time series of data, or there's a few demos that you can use. You can see how we go about selecting a baseline, how that has an impact on the threshold, how that dictates which events are determined where in the time series, how intense they are, and you can twist all these knobs and see how it reacts in real time. You can zoom in on big events. It'll show you how we determine the intensities, the durations, and all that sort of stuff. So that's one thing to get started. If you're not interested so much in the definition and how that looks, if you would rather just access the results that are already calculated daily, you can go to the Marine Heatwave Tracker. There's the QR code in the bottom corner and the URL if you don't want to use a QR code. This then provides daily maps from now. It's operational, so it's about a 2-day delay to real time, back to 1982, January 1st. You can load them. It's like Google Maps. You can scroll around and you can click on individual pixels to load up the time series. You can explore however you prefer, and you can download all those data to use for your own purposes. This is used in science as well as in journalism. I see these figures popping up on occasion in posts about marine heat waves. There's also a Twitter account that posts about this stuff. If you're interested in calculating or working with marine heat wave statistics yourself, it is available. There's a library available in all 3 of the major programming languages used in science, so Python, R, and MATLAB. I am the maintainer, the lead author of the R iteration of the language. So if you do go to the GitHub and you post any issues, it will likely be me that you're talking to. So please be very friendly. And then lastly, for anyone that just doesn't know where to get started and they really want to learn more, I would highly recommend, as a first stop, not the only stop, but as a first stop, going to the Marine Heatwaves International Working Group. And so here's their website. There's the link at the bottom. It's very actively maintained, and they have a lot of really good resources and publications that are tracked. And from there, you should be able to find out all sorts of interesting stuff. So at that, I will leave it for any questions. And thank you very much for listening.